Everyone, I'm Dong-Eon Kim from AIoT Lab at Pukyong National University. Today, I'm going to present about IoT-based quality monitoring system using computer vision and air quality sensor. My present is four parts. First, introduction. Second, IoT-based meat quality monitoring system. Third, experiment and result. Finally, conclusions. Let me first introduce my research objective. Basically, the research is about measuring the status of livestock products in distribution and sales and automating and systematizing them. That way, the cost of management can be reduced while consumers' health can be protected. We have also established the standards for managers and consumers to identify freshness intuitively based on their experience. This means that measured data is electronically recorded and used to determine meat freshness using quantifiable indicator. By doing so, we hope to provide services that have never been offered before and that can be applied in the real world. In the same way that the user relies on the sense of sight and the sense of smell, our system also incorporates an embedded camera and a gas sensor. As a result, we designed a miniaturized sensor tag equipped with camera and a gas sensor. Here is how the system is currently set up. Data is collected through a camera and a gas sensor, which is located in the package where meat is stored. In order to communicate with the gas sensor, the microcontroller unit utilizes the I2C. Moreover, SPI is used for communication with the embedded camera during the Wi-Fi environment. The measured data is stored on the Raspberry Pi's local server. Through the Firebase server, stored data can be accessed by the mobile phone application. We also use a specially designed box for the precise gas measurement. This picture shows pork measured for 5 days in the system. As you can see in the picture, the bright red meat turns dark brown over time. Also, several pork packages are being measured simultaneously and gas sensors are also being used. Due to the lack of public data sets, augmentation was used to supplement the data. We use augmentation to augment images. It provides various image conversion algorithms and each processing speed is very fast, so it is used for deep learning processing. You can check various result value by setting the list of functions to be applied and the probability that the function will be applied. In augmentation library, we use the various filters to add the data and use it for training, so that in the augmentation input, the image parameter is entered and the transform function outputs the image key value. It is fact that the amount of myoglobin and oxygen in meat affects each color. There is a high concentration of oxygen in oxymyoglobin and less than 1% in methmyoglobin. If there's no oxygen, it's deoxymyoglobin. The meat turns purple after being slaughtered, then pink and the brown after is exposed to oxygen, and this process is called oxidation. In the picture on the upper right, it is confirmed that the pork changes from light coral color to a sadder brown color. In the process, bacteria convert it into alcohol and aldehyde, creating CO2 and H2 as byproduct. An article published in Letter Applying Microbiology states that CO2 makes up most of the gaseous components released during meat decomposition. Here is the analysis of the gas used the headspace method. Check the gas composition by analyzing the gas composition generated during the heating. Furthermore, a SOTA model, DeepLab, is used to automatically classify an additional learning target and predict its state. DeepLab is a semantic segmentation architecture that captures context for multi-scale object segmentation and a feature a high-performance encoder-decoder network. Here is the encoder part. Arbitrary resolution features are extracted using atroz convolution. Atroz convolution refers to a form in which the filter window is spaced internally to increase the field of view of the filter in the basic convolution layer. In other words, when using atroz convolution, the respective field is increased while maintaining the same amount of parameters and computation as the existing convolution. The atroz convolution appears in the center of the top. After that, atroz spatial pyramid pooling is applied. This is a method of applying atroz convolution with different dilation rates from the feature map in parallel and then combining them again. In the figure, the dilation rate is varied from 6 to 24 and applied so the various respective fields can be seen. ASTP can be used for extra feature maps of various sizes and mix them. As the receptive field is fixed, we can see intuitively that there is a descent approach compared to fully convolution networks where small objects are ignored and perceived as old. If you go to the right of the encoder section, you will see a depth-wise separator convolution. Depth-wise separator convolution is a method that separates and processes the spatial and channel dimension of the existing convolution filters at the same time. Even if the two axes are processed separately, the final result is in the process of both axes, so it can replace the role played by the existing convolution. However, this structure is used because it can dramatically reduce the number of parameters and the amount of computation and compare the existing convolution operation. The decoder and uses encoder-decoder with atroz convolution, which is the third structure in the figure, is the upper center. Performed by bilinear upsample on the encoder features from the encoder, then one by one convolution is applied the feature map from the middle of the backbone network to reduce the channel. After concatenating these two, after going through 3x3 convolution layer, the output from the last 1x1 convolution is linear upsampled to the original input size. The deep lab whistle model applied has uses exception as each backbone network. By using deep lab, you can receive information about an observation object if its state changes to rotten. The right image shows the outcome of using deep lab on the observation. The MobileNet characterized the MIT based on measurement made with the embedded camera. The MobileNet performs point-wise convolution through depth-wise convolution. Upon completing two depth-wise convolution, the output classes are produced through a global average pooling layer. Through normalization, CO2 and TVOC values measured by a gas sensor are segmented for data learning. Afterwards, 1D CNN models are used for feature extraction. The 1D CNN model is trained by inputting labeled time series data from the mobile network and data measured by gas sensor. Figures on the right shows the 5 days temperature data at 20 degrees for 5 days. Freshness rate lasts for 10 hours on average, and after that, maturation takes up to 80 hours. After 80 hours, the food becomes unusable due to its deterioration. Our team conducted additional experiment with market available meat. In order to detect segmented color changes, HSV values were analyzed using computer vision. For your information, HSV is a color space technique commonly used in image processing. After consulting with the manager and sales staff of large supermarkets, the spore set was labeled based on the smell of the food and its visually changing state. According to our finding, freshness of the product lasts 15 hours, ripens for 80 hours, and rots after that. Our study showed that a saturation value represents an overall state change based on the time series flow among HSV convolution values. The 1D CNN model we used for prediction looks like this. Activation of value occurs after the feature set passes through a 1D convolution layer. After passing through the flattened layer, the feature filter is trained about a hidden layer consists of 128 to 256 to 128 layers. It then passes through softmax and output the food state. As you guys can see, there are occurrence and loss curves from the 1D CNN model after training and validation. It is estimated that the average accuracy is 99.3%, and the training, validation, and test sets are divided in the ratio of 7 to 1 to 2. For fresh and ripened stage, it shows 100% accuracy, while while for rotten and ripen sections, it displays 98.3% accuracy because of an error. The developed model can be accessed via a mobile application. By using the DeepLab V3 algorithm, the app identifies segmentation information. Whenever there is a change in the state of measurement target, for example, rotten, etc., an application will receive this information. The right image shows an example of how the application interprets the data and the data can be checked. This article presents a sensor fusion system based on an IoT-based system that automatically monitors meat quality. Measuring the state of meat with the sensor fusion has two advantages. One of the advantages is that it utilizes quantitative data indicator and has objective criteria. Additionally, instead of using one piece of data, the data complete each other and serve as the basis for the model. Our team developed a user-friendly application serving using a computer vision system that uses deep learning. There is a 99.43% accuracy rate for a deep learning model that predicts the three quality stage. It is our intention to continue experiment with data augmentation going forward. Our goal is to improve the quality of our data by developing algorithms and updating deep learning models based on different type of data. In my last slide, I would like to acknowledge the participation of my advisor, Professor Wan-Young Chung. Thank you for your attention, and I'm looking forward to your comments.